Okay, so hello. So in this film, I want to talk about uh, quadratic functions. So in Swedish, andra grads funktioner, and their graphs. Okay, so I have this set up with sliders. So it's showing the graph here, y equals 1 x squared plus 1x plus 1. Normally we would not write these ones. We would normally write x squared plus x plus 1. Okay, but here these ones here, these are the values of the sliders values here. Yeah. So to actually set this up, I typed in I typed in y equals a times x squared plus b times x plus c. Okay. And then when I hit enter, then it gives me these sliders here. So the reason I'm kind of showing this is that I think that the slider function in GeoGebra, it's a really great feature. So I strongly recommend that you try this out. So if we just hit play here, then what it does is shows an animation in which the value of a is changing. So it's showing the graph here. If I just press pause, then this graph that is on the screen right now, this is the graph of negative 0.93 x squared plus x plus 1 here. Yeah. So what we see here is that when this value of a, when this is a negative value, we see that we have this inverted U shape. It's kind of like an upside down U shape here. And that's the case whenever we have a negative value there. And then you see here, it's broadening out here as we get closer to 0. Then when we hit 0, then at that moment, we have basically, in that case, it's not a quadratic function. It's actually a linear function. It's just y equals x plus 1. Okay. And when the value of a is positive now, then the quadratic function has this U shape. Yeah. So so we see there some examples of graphs of quadratic functions where we're just fixing these values of b and c equal to 1 and seeing the effect of the value a. Okay. So one thing that we can say here as well is that when you get a larger value for a, you get like a steeper U shape. Okay, because you can think that the value here for any given value of x, that is going to be equal to y, and the y coordinates, those are in the vertical direction. So then that means that a larger value for a is going to mean that the y values are increasing faster when x increases. Yeah. If we're thinking about positive x values here. Right. Okay, so let's maybe fix the a at 1 here. Okay. And then maybe it's easiest to look at c next. Okay. So we see here that the value of c is actually equal to the so-called y-intercept. That is where the graph cuts the y-axis there. So you see there it cuts at 3.6 when this value of c equals 3.6. So again, the if we just keep this, I just see that this is 0.9 here, but let's not worry about that. We see here that if we hold these coefficients fixed and just vary the c value, we see that the c has the effect of sliding the graph up and down in the vertical direction, such that it cuts the y-axis here at this c value. Yeah. So then if we, maybe I can just start again with y equals x squared, and then plus d times x, and maybe plus 1 here. And maybe just remove that one, just so that we're just changing the value of b there, keeping the other coefficients at 1. Because when we change the value of b, which I've actually just called d for now, but we see that this is a little bit more it's not such a straightforward pattern. Okay. So what can we say here? Well, as the value of b changes, then the graph still maintains its approximate shape, and it still maintains the same y-intercept. But the vertex, that is the minimum point, that will appear in different places for different values of b. Okay. Now, an interesting case is when the value of b is 0. So I can basically get that effect if I just delete that term. So if the value of b was 0, we just had ax squared plus c here, then, oops, maybe I just start a new tab here. Sorry about that. Right, so if I just start with y equals a times x squared, and then plus c, just so that I'm setting the value of b equal to 0, then we see that the values of a and c can change. Okay. We can vary those values and play the animation, but the vertex, okay, that is this turning point, which can be either a maximum if the shape is this upside down U, or a minimum if it's a regular U shape here. This vertex, okay, is always on the y-axis here. It always appears when x is equal to 0. Okay, so maybe that is the kind of simplest generalization we can say about the b value, that when it equals 0, then we get this this vertex on the y-axis. Okay, so you see here with these quadratic functions and their graphs that it's a more complicated situation than we had for the linear functions in Math 1C, because we have these curves, and there's kind of a little bit bigger variety in terms of the graphs that we actually see. Okay, so I think I'll make a cut here and then continue in part 2. So in part 2, I'm going to talk about using graphs to solve quadratic equations, that is Andragoras Ekvationer, and to also talk about the zeros of quadratic functions. Okay, that is the null stellen until Andragoras function. Okay, super. Thanks for watching. See you in the next part.